Okay, we can start now. So, currently we are in the week 10 of Introduction to Material Science and Engineering course. And we saw that a lot of concept has been covered in this particular week. One section was related with the phase diagram, where we discuss about the heat treatment process, for example, tempering, mark quenching, and hypereutectide and hypoeutectide steel, how their TTT diagram will vary. So these are the concepts we have covered. Okay. Before I start with this particular week 10, there was one question in the last week by one of the learner who joined this particular doubt solving session. The question is why the full annealing is in hypereutectoid state is performed between A1 and ACM. Couple of things we have to see. We'll try to answer this question. Hypereutectoid steel is there, and we are talking about the full annealing. What is the meaning of this? These two things. A1 and ACM. A1 is a line, it's a temperature of this particular line, we call it to be the A1. ACM is this one. Okay, this is ACM. And this one we call it A3. So our current question is related with the hypereutectoid steel, that so we know that the carbon percent will be more than 0.88%. So we are lying somewhere over here. This is the composition where we are lying. Now what is a full annealing? Annealing is a heat treatment process where we are heating the sample, and we are heating it to one can say that to reduce the stresses, whatever the stresses that was there before, and to form a new phase. From here, let's say currently I am at this particular temperature, I will heat it, I will anneal it, and then I will slowly cool, slow cooling process. So what I will do, we'll start from the room temperature, let's say we are taking the carbon percent more than 0.8, we are heating it, and then after that we are slowly cooling this part. This process is known as annealing. This is a soaking period, temperature, and this is time. We are heating at particular rate, holding, and then quenching, and then slowly cooling it down. Now why? The question was that why we are not doing it above this particular ACM? Why it's always that the engineer prefer to do between ACM and A1. While it is not the case with when we talk about the hypereutectoid. First of all, let me tell you, this concept is not covered in our course, but since it was asked, so I think it's important to answer this question. So if I talk about the annealing, so what happened in the case of hypereutectoid, we usually perform it above A3, somewhere over here, this particular temperature range. But when we come to the hypereutectoid, then we perform in between. Now what is the reason behind that? The reason is very simple, that if I go to the high temperature where we are getting single phase of austenite, and now I am trying to cool austenite, the first thing what will happen, let's say this is at this particular temperature I am cooling it, the first thing it will form is the austenite plus cementite. Now this formed phase, it will go to the grain boundary, they will form and also it will form the continuous network. Now this continuous network, which is formed by the Fe3C, it's very brittle. So if my microstructure is something like this, where cementite Fe3C is at the grain boundary, it's forming the continuous network, it is a brittle phase. If the fracture start from here, it will propagate. So we cannot do slow cooling from here. One can do the fast cooling. In that way, they can avoid the formation of the cementite at the grain boundary to a certain extent. But when we are talking about the annealing, our rate of cooling is slow, and that slow cooling is sufficient enough for the cementite to form at the grain boundary, and it will form the continuous network. To avoid that, if this was the case when we are at this, we went above the ACM, the case was the temperature is above ACM. Now if I go somewhere in between, I'm going now what at this particular temperature, let's say I took my steel from room temperature, I heated it above this particular A1 temperature. Now what is having is that there is a phase of alpha and there are cementite phase like this. It will be like this one. The important thing is that when I'm heating this at this particular temperature, then here the continuous network which was there before, it's no longer there. And now if I try to cool from here, the temperature, the time is not sufficient, and also the cementites are not will not come to that. They will come at the grain boundary, but they won't be able to form the continuous network because they are separated. So continuous network of cementite is eliminated in this case, and this is the whole reason why we are performing the for the hypoeutectoid steel we perform in between them. Now you can ask me why not for the hypoeutectoid, why not to perform in between this. The main reason is that here the alpha which is there, it is not brittle, so even if it come at the grain bond, it's not a problem. But cementite was a problem. So if I go over above this particular temperature, it's fine, it's good for us. We can at the grain boundary the ferrite phase can come. That's the reason why when we talk about the annealing for the hypo, we do at this particular temperature above A3, while for the hypereutectoid we do at above A1 and between ACM. Is it clear? If not, let me know. Since it's not covered in the class, but it was asked by the student, and last time I was like little bit confused with the terms, so I was not fully able to answer that part. Okay, great. So since it's clear, now we can go ahead with our week 10 discussion. Let's see the list of the concept that has been covered in this particular week 10. The concept that has been covered is, we discuss about the quenching and martensite. Austempering and bainite. Austempering will form the bainite. Then we discuss about the tempering. We got the martensite, but we want to reduce its hardness because it's so brittle. We want something useful, so for that we did the tempering. Then we went for the residual stress part, that okay, in quench steel the residual stress can come. Then we discuss about the mark quenching, how we can avoid those residual stresses. Okay, we discuss about the TTT diagram for the hypoeutectoid and the hypereutectoid steel. And then TTT diagram of the alloy steel, we discussed how the addition of the alloy, for example chromium, those things is going to affect the TTT diagram. We discussed the term hardenability, which is different from the hardness. So this term hardenability and hardness, they are different from each other, they are not equivalent. Later on we discussed about the, now this section of our week 10 is based upon the heat treatment. Next section we discussed about the strength of the mechanical properties of the steel, of the material, where we discussed tensile test, how we perform plastic deformation. So they've changed that the concept, like will the plastic deformation will change our crystal structure itself. So that type of discussion we have did. We discussed about the slip, we discussed about the resolved shear stress and critical resolved shear set, and at the end, very important law, we discuss about the Smith law. Before I go to the solving the questions, I would like to ask you, do you have any doubt in the list of the content that has been covered for the week 10? You can also feel free to reply in the text. If you are comfortable, you can also unmute and interact with me. Both. Great. Seems like there's no doubt. Let's go to the next. Let's go to the solving question. Questions is very easy. Let's start with the match the pair. Austenite, ferrite, and martensite. We have to find their crystal structure. So, what about the austenite? Austenite phase, when we are talking about that at the high temperature. This is austenite. This is Fe3C plus alpha, which is ferrite. Okay, so austenite we know when we go to the high temperature around 725, about 725, when we are talking about the 0.8%. Austenite is the FCC. Sorry, austenite is a BCC. I think I am making a mistake. Austenite is not BCC. Yeah, so austenite is a FCC. Alpha ferrite is BCC, and martensite, it's a, how can I forget this thing? Just a minute, guys. Yeah, right only. Fine. Austenite is the FCC, and then we have BCC, and martensite is the BCT. So we know that when fast cooling, quenching, we can say fast quenching, we will get the BCT. When we are doing slow cooling of the austenite, we are getting BCC. BCC body center cubic, BCT body center tetragonal. Okay, so this is BCC, this is FCC, and then when we go to the delta ferrite, what would be the delta ferrite? Delta ferrite will again be BCC structure. Okay, so austenite here is a FCC, ferrite is a BCC, and martensite is a BCT. Very important. This type of questions are mostly it come in the GATE exam. We have to remember all this thing. Not only from the exam perspective, this is the very basic part which we all of us should be aware of. Any doubt in this? Let me know. If not, let's move to the next part, question number 2. It's a true and false type. Yeah. Martensite transformation depend upon the time and temperature. When we talked about the TTT diagram. Okay, what we saw that above a temperature it's a austenite. Then we have the cooling curve. We have the C type of curve, and at the end we have martensite. This is the martensite. Okay. Here is the, again it's a gamma, but it's unstable gamma, and here we can say that the ferrite and all, that pearlite phase will come. What we see that when we are talking about the martensite start, this is the temperature at which martensite start to form, and this is the temperature where martensite finish. What we can see that here the C curve is there. It is indicating that the transformation is time dependent, time and temperature dependent. Here we can see that there is no C curve. The fraction transform will only be depending upon the temperature. It will only depend upon the temperature, not the time. You take the steel, you take the austenite, cool it very fast. Let's say you cool at some temperature somewhere between this. What you have got, that certain has been transformed. It will not take a time to transform. Instantly it will transform. You decrease the temperature more, the martensite fraction will increase even more. And after ms, it will be completed. So martensite temperature transformation depend on both temperature and time? No, it doesn't depend on the time. It depends upon the temperature. Okay. So transformation rate, for example, so answer here is false. If they will only say about the temperature, then we are fine. We'll put it as a true. One more thing, transformation rate. Transformation rate will be it is respect to the time. Okay, how much fraction has been transformed? Transformation rate. Okay, fraction of transform fraction to the martensite. It is dependent of the temperature and it is independent of the time. So the transformation rate is always fixed. Transformation rate, like you just put at particular temperature, the transformation is done. Okay, it doesn't depend upon. So overall, we call it as a athermal. Magnetic transformation is athermal. It doesn't depend upon the temperature. It doesn't depend upon the time. But the fraction transform will depend on temperature. Okay, that is, since we are talking about the rate here, rate is not depending upon time or temperature. Now let's go to the C part. The C by A ratio in the martensite unit cell is equal to 1. What we have said, BCT. Martensite is body center tetragonal. Will the C by A for the tetragonal will be 1? Very good. It's a false, right? Very good. If C by A in martensite, we are talking from this perspective, is equal to 1, then it's not BCT anymore. It will be BCC. While if C by A is greater than 1, then we can say that it's a BCT. And so this is nothing but a alpha ferrite. And this is the martensite. Clear? Very good. Let's go to the next part, question number 3. Quenching produces a very hard but brittle microstructure. Martensite is very hard. More is the hardness, more brittle it is. So what do you think? It's a true or false? It's a true, right? It is very hard as well as the brittle. And for this only, we cannot use the martensite. Its application wise, it is not usable. What we have to do, we have to reduce its hardness, we have to reduce its brittleness, and for that only we perform the tempering step. What we are doing in the tempering, for example, we went to the austenite. This is the temperature, this is the time. We austenized it for a time period. See, we went to the high temperature, we went to the phase where austenite is there. We are putting it for a time. This period is known as austenization. Now we are quenching it. So what we have produced? We produce the martensite. Now martensite is very hard. It's very brittle. What we'll do, there is a process of tempering. We'll heat it and we'll keep it at low temperature, and what we'll see that a martensite will convert to the ferrite and cementite. Certain fraction of this will convert. Now they will have the hardness will be lower, brittleness will be less, right? So this thing will happen. So for that only we are performing the tempering. Clear? So with that we have solved the C part. Let's go to the next part. Martensite transformation involves significant composition change. Are we changing the composition? Well, the composition will change if I am cooling from here to here. Fast cooling. Answer is no, right? Yeah, it's a false. Very good. So here we are not changing the composition. Okay. If we are starting with the 0.8% carbon, you then you quench it. Let's say austenite has 0.8%, then martensite will also have 0.8% carbon. We are not changing the composition in any way. The nose of the TTT curve, the nose of the TTT diagram represent the slowest transformation rate. This again transformation rate for martensite. Let me explain this question. What this question is saying. Again, let's only talk about 0.88% carbon to avoid any additional point over here. This is martensite start and this is martensite finish. I started with this austenite. This is temperature and this is time. I started with this point and let's say now I'm cooling it like this. One can say that will I get the martensite? I'll get lot of phases. Austenite I will get, austenite will convert to the ferrite and cementite, right? Will not get the martensite. What we have to do for the martensite to get? We have to quench it. Fast cooling, right? Quenching. This was the case 1 and we got that case 1 is failure because we'll not get the martensite, we'll get some other phases. Now, this is the where we are getting the martensite second one. Now, this. Will I get martensite here also? It is not crossing the C curve, right? Third one. We'll get right. That is also true. How about if I do very close to the nose? I am not cutting any of the phases. For example, austenite was converting to the perlite phase. Okay. Here will also I get the martensite because the reason is that I am not cooling. I'm not touching any of the other phases over here. Now, a question. Case 2, which is this one, case 3, which is this one, and case 4, which is the last one. Among them, 1, 2, 3, 4, which one is having the lowest cooling rate? Here cooling rate is like this. Here cooling rate is this. And this is the cooling rate over here. Which of them is having the lowest cooling rate? Lowest cooling rate means that it will take more time, right? For example, see, first one took this much time, second took this much time. Okay. So the case 4 is taking more time, so it is slow. It's not the one, right? I'm talking about in between 2, 3 and 4, very good. So you can tell 1 also, but our competition is for the martensite only. We only want to get a martensite. If I go with the 1, I will not get the martensite, right? So as you have answered 1, yeah, very good. The answer is 4 over here to get the martensite. So the nose of the TTT curve is saying that, is putting the restriction that, okay, this is the slowest rate you can go and get the martensite. Among all of them, 2, 3 and 4, we can get martensite. But which is the slowest will be defined by the nose. The nose of the TTT curve, TTT diagram represents the slowest transformation rate for martensite. And this is okay. Great. Since we are any doubt in this question number 2, let me know. If not, we'll move to the next question, question number 3. Okay, no need. Yeah. Which of the following is not a characteristic of the Martin-City transformation? First one, extreme rapid transformation. This is the characteristic, right? This is true. Composition change involved. Very good. The right answer is option B. So the composition change is not there. Whatever the composition we are starting, if we are starting with the 0.8%, then it will go with the 0.8%. Transformation rate independent of time. This is also true. Diffusion less process. Okay. Again, I should be more precise here. Long range diffusion. Oh, sorry. Any long range diffusion is not there. Okay. From the long range. But I should write the true, right? So short range. Long range diffusion less right away. So what is happening in the Martin-Site transformation when we are doing from austenite to Martin-Site? The diffusion is not happening. We have that to we have to be very precise. The long range diffusion is not happening. The short range diffusion will happen. See, for any transformation, we have seen in the last week and last to last week the process of the diffusion. So for any transformation, phase transformation, we need the diffusion to occur. Someone is telling that there is no diffusion involved in the Martin-Site. So subconsciously they are thinking from the long range. Okay. If they are saying absolutely no diffusion, then it's a wrong statement. Diffusion will be there. A short range diffusion will be there over here in the Martin-City transformation. So when we are saying the diffusionless process, we are thinking from the perspective of there is no long range diffusion is there. Okay, very good. Option C, composition change will be involved. That this is the incorrect answer, and so this is our right answer. Any doubt in this? Let me know. If not, let's go to the next part, question number 3. We have 3 processes: annealing, normalizing, and quenching. Annealing we have discussed. Let's discuss it again. Heat treatment process, take your steel, whatever the composition, from room temperature, the temperature which is above the austenite. Okay, then hold it, and now cooling. Cooling is like very slow. This is annealing. Cooling is little faster. It's a normalizing. Very fast. It's a quenching. Okay, it's clear to all of us. Slowest is the annealing, then normalizing, and then we are getting the quenching. Annealing. Okay, first one is going to match with the slowest cooling rate. Very good. So slowest cooling rate is D. Let's go to the second one. Normalizing. Normalizing will be the. What about third one? D. Let's answer that first. Quenching. Quenching will be the. Among these, which one will be the quenching? Yeah, very good. It will be the E. Okay. So quenching is E. Annealing is the slowest cooling rate. Now, see the other options. Produce fine perlite, produce coarse perlite, produce martensite. Which of them will produce the martensite? C is going to match with. Among this annealing, normalizing, and quenching, which one will produce the martensite? To produce the martensite, we have to cool it extremely fast, right? One option can have more than one. One question can have more than one answer also. So here, a 3 will give me C also, produce martensite. So here it will be C also. Now, see, we have a TTT curve. This is let's say perlite. I'm cooling from here. I'm going with slow cooling rate. I'll get perlite. It's an annealing process. Second, I'm cooling faster. Again, I will get the perlite. But this process is normalizing. The thing is that when you are cooling at a faster rate, cooling rate you are increasing, what you are decreasing is the time. So for the grain to grow, grain growth, the time is not sufficient. The grain growth will not happen. So if you increase the cooling rate, grain growth will not happen. It means that you are producing the fine microstructure. So here, when we are going to the fast cooling rate with the normalizing, here we are producing the fine perlite. While when the cooling rate is very slow, here we are producing the coarse perlite. Great. Now we can answer the question. Now we can answer the normalizing also and the annealing also. So annealing is going to produce the option B, right? Produce the coarse perlite. Normalizing will produce fine perlite. It's a. It's clear. So I know I made little bit the question. The way I made the question is little difficult in a way that one can match with the multiple. But this is just for our understanding, to test our knowledge, and to know that okay, this type of questions can also be a part. Any doubt in this, please let me know. If not, we'll move to the next part. Question number 5. Okay, this question 5, fine. Bainite form when austenite is, when the bainite will form. What is a bainite? We, as you can see, a couple of phases we have not discussed. In the phase diagram, bainite is one of them. This is the martensite start. Till now we were cooling them at a particular rate, like this, then like this, and once we are quenching also. If I want to form a bainite, what I will do, I will do Aus-tempering. The process which I am going to explain now to you is a Aus-tempering process. I'll cool it fast, but I will keep it above the martensite. Okay, and what I will do, I will make it stable at this particular temperature, and I will give a sufficient amount of time. Now the structure which we will form, it will be bainite. How it is varying from the other. Bainite also has the ferrite and cementite. Sorry, alpha ferrite. Perlite also has the ferrite and cementite. You will see that both of them are having the same thing. What is the difference between them? The difference is in the microstructure. Here, they are forming the lamellar structure, like ferrite. Then in between cementite, white portion, let's say I'm putting cementite. This is again ferrite, then again white portion, then this is again ferrite. So ferrite, cementite, this. While in the bainite, the cementite is coming like a needle. So I will have an entire structure where alpha ferrite will be there. Okay, and in that a needle structure will come like a bainite. It will be like a needle. It will be very sharp. So they are differ from the appearance. So within a grain you will get the sharp needle type Fe3C cement. This is where the bainite differ. So the difference is in the microstructure. And why we have produced bainite? It has more hardness. See what we did, when we cooled it very fast, temperature is low. When the temperature is low, growth is not there much. But what is there? It's a nucleation. So nucleation is happening fast here, but the growth is not happening. So, so this is how it will go. Okay. So with that, we can answer that. Our answer will be quench below. Yeah, here the quench below the nose, but above the MS, and hold isothermally. So option C is the right answer over here. Great. Okay, great. Let's go to the next question, question number 6. So here, what we have. So here what we have is microstructure and the characteristic of them. Okay. We have a perlite, bainite and martensite. We have to find which of them will be the better match. Let's go one by one. Let's start with the perlite. So perlite, alternate plate of ferrite and cementite. That's absolutely true. We know about this. It's a lamellar structure. So first one is going to match with the A. Let's go all of them together. Fine needles of cementite in the ferrite matrix. No, perlite is not that. What it is? It's a bainite. So let's for second also. Second we can go that it's a B is the right answer. It will be needle-like structure. Let's go with the C option, body center tetragonal structure. What is a perlite is having? Perlite is a microconstituent. It is made up of two things, ferrite and cementite. Right? It is made up of two things. Same is for the bainite also. Okay. When we are talking about the martensite, we have single phase, which is tetragonal structure. So third can be matched with the C. It's a BCT. Now fourth one, formed by slow cooling. Slow cooling will not be formed by the martensite. In bainite also we saw that we went with the fast cooling because we have to get below the nose. So what we did, it's a perlite. So perlite is the one which will form by the slow cooling. So option D will also be there. Let's move ahead. So we discuss A, B, C and D. Now E, formed by the isothermal transformation below nose. Isothermal transformation below nose, we can say that bainite will be the best choice for it. We are going below the nose. I should also write somewhere below nose and above martensite start. Now last one, formed by the rapid quenching, we know it's a martensite. So option third one, martensite will match with this also. So we can see I made the question in a way that one of the option will be matched with the multiple. So each of them is having two. Very good. If you're facing any problem in this, any doubt, please feel free to comment in the channel, or you can also ask in the Q&A. Okay, so this was a good question. Let's move ahead to the next part, question number 7. We'll do it one by one. Tempering is performed above the eutectoid temperature. Answer is false, right? We usually perform the tempering above the martensite and below the eutectoid temperature. Okay, if we go above the eutectoid temperature, then what will happen? Austenite will form, right? And which we don't want to form the austenite. The tempering process is to convert martensite to the ferrite and cementite. So with that we can say that it's a false. B, tempered martensite tempered martensite has better toughness than the Asquench martensite. We are talking about the toughness. If we reduce the brittleness, the toughness will go high. And we know that the Asquench martensite is more hard. It's too brittle. While the tempered martensite also had the composition of, also had the phase of the ferrite and cementite. So with that we can say that yes, it is true. Right? Decrease the hardness, the toughness will go more. See, the hardness of the hardness of the tempered martensite can be lower than that of the normalized steel. The hardness of the tempered martensite can be lower than that of the normalized steel. Answer is can. The, the they use the can word. See, again, one need to be very precise. The question, the way it made it, the question is not that. Usually, larger scale, tempered martensite will have more hardness than the normalized steel. So can, since they use the word of can, so it's a, the question will be valid right now. So the tempered martensite will definitely have the more than the normalized. So answer is false here. Okay. But again, it depends upon at what temperature you are tempering it. It is possible that you can go at high temperature and you can bypass this. So since the can word is there, so it's a, the question is in the safer hand. But one shouldn't make the question like this. Now the next part. Both the temperature and the time affect the final properties of the tempered martensite, tempered steel. Both the temperature and the time. The answer is right. Go to the high temperature. Increase the temperature, the transformation will be more faster. The more ferrite and cementite will form. Time, hold for the longer period of time, the more the transformation again will be proceed further. So here the answer is true. Let's go to the D. Let's go to the E. Tempering completely eliminate all the hardness gained from the quenching. Tempering completely eliminate all the hardness gained from the quenching. Answer is false. Right. So with that we can see that these are the answer. Let me write it. False, true, false, true, and false. If any doubt, let me know. If not, let's go to the next question. Question number 8. Fill in the blanks. The process of heating steel to form austenite before quenching is called. Okay. We discuss this part. For example, I'm heating, holding for the period of time, and then I'm doing the quenching process. So they are calling, what is this process? It's a austenitization. Austenitization. Tempering transform martensite into dash plus what? Okay, so we can say that it's the tempering will transform martensite to the ferrite and cementite. Next one. The two main variable in the tempering are two main variable in the tempering, it's the time and the temperature. To what temperature we are tempering, and at that particular temperature for how much amount of time we are tempering it, right? Now D. Higher tempering temperature and the longer time result in the dash in the hardness and dash in the brittleness. The hardness will go down. If we are increasing the temperature and time both, so what is happening is here is that the more ferrite and cementite will form, so the hard martensite fraction will decrease. So here we will get the hardness to be reduced and ductility will be the more or increase. With that we have solved the question number 8. Let's go to the next part, question number 9. If any doubt, let me know, okay, in between. Tempered martensite consists of tempered martensite, alternate plate of ferrite and cementite, fine particle of the alternate plate of ferrite and cementite, it's we get in the pearlite lamellar structure. Fine particle of cementite in the ferrite matrix. This is our answer. The matrix will be by the alpha ferrite. And in that you will get the fine particle of cementite. Option B is the right answer. Now let's see third part. Body center tetragonal structure, no. Right. The transform thing is not the tetragonal structure. It will get the pure ferrite. Option is obviously no. A, C and D is wrong. B is the right answer. Let's go to the next question. Question number 10. Match the pair. Volume change during transformation. We know when we are going from the austenite to the martensite. When we are going from the austenite to the martensite, a phase transformation is taking place. Along with that particular phase transformation, the volume is also changing. Why? Austenite has the FCC structure. Martensite has the BCT structure. FCC is a close pack, so density of austenite is more and density of martensite is less. Volume will follow the different trend, just opposite trend. Okay, so the volume of martensite will be more and volume of the austenite will be less. Right. So when we are going from the austenite to the martensite, we are going from low volume to the high volume. So the volume is increasing over here. The transformation which is FCC to the BCT, the volume is increasing. So here the volume change during the transformation is FCC to BCC, right? Second, surface cooling rate. Surface will cool always faster than the bulk, than the core. So the option will be the A. Residual stress form. We know that since surface is cooling faster and core is cooling slower, so this will lead to the generation of the tensile stress at the surface. The reason is clear that at the surface the martensite will form first. The volume has already expanded. Now the core is trying to transform. So inside there is a tensile stress. Sorry, inside there is a compressive stress. So outside will be the tensile stress. Right. Like if the outer layer, which is martensite, now inside is also the martensite start to form. So what is it, it's trying to increase the volume. It's pushing it, but then again it's getting back. So what is getting, like, it's stuck. The stresses is there inside, and surface is facing the tensile stress. Right, they are facing the tensile stress. So with that we can say that the right answer will be the C, A and B. Any doubt in this, let me know. If not, let's go to the next question, question number 11. What is the primary purpose of Mach quenching and Mach tempering? This is the question. What is Mach quenching and Mach tempering? First of all, we have a TTT diagram. It goes like this. Just now we discussed that there is a residual stresses is there, right? Now if I am cooling it from this particular temperature, the process of Mach quenching is what? Both are same. First of all, they they differ in the name, but both the process are same only. I am cooling it fast. I am going below the nose, but I am just above this ms. Now I am stabilizing at this temperature for a long period of time. So what will happen? this particular temperature, just above the martensite start, I am holding it for a long period of time. So now and the core, the surface and the core, they both will be at this particular temperature. Let's say T1. So their temperature will equalize. Now if I try to cool, now they will give me the martensite, right? So now what is happening? What we did is we somehow we tried to reduce the temperature difference between the bulk and the surface. And that if the temperature difference is not there that much, then we can reduce the quenching stresses. Okay, so the primary aim for this thing is to minimize the residual stresses and quench crack. Option B is the right answer over here. Let's go to the next question. Question number 12. Is mark quenching, the quenching is interrupted at what temperature range? In mark quenching, below martensite finish, between martensite finish and the martensite start, above martensite start but below the nose, above the eutectoid temperature. Obviously, D is obviously incorrect. We are not doing below and we are not doing between. We are doing just above the martensite start. That is option C is the right answer over here. Okay. Any doubt is here? Let me know. Okay. See, we are holding it above the martensite start and martensite finish. This is the main. This is the question number 12. Let's go to the next question. Question number 13. No, this is a little interesting question. The same type, like one can have more than one answer. So 1, 2, and 3. Conventional quenching. Produce martensite with high residual stress. Conventional quenching means went to the austenite, directly quench. Okay, no, we are not doing any mar damping, mar quenching and all. Okay, so it will produce the high stress. Option A. Performed after martensite formation. Obviously, mark quenching, it not perform after. The mark quenching is also the one of the path by which we form the martensite. So the tempering is the one which is performed after the martensite formation. So option in box 3, the B will come. Rapid cooling to the room temperature. Again, it's a conventional quenching. Option C. C will fit to the 1. Interrupted quenching above MS. Interrupted quenching above the MS. This is nothing but we discussed just now that it's a mark quenching. So option D will be the right answer over here. Improve toughness of the martensite. To increase the toughness, what we do? We do the tempering. The martensite we have now will temper it, will go to the high temperature and we will get this answer. So option E is the right answer over here. So with that, we have solved this question number 13. If any doubt, you can let me know in the comment box or in the chat. Let's go to the question number 14. Okay, fill in the blanks. Common alloying elements like chromium and they are dash solute in the steel. What are they? Are interstitial or substitutional? We know that they are substitutional. So the right answer will be the second option. In plain carbon steel, bainite can be produced by continuous cooling. Can we produce the bainite? What we did for the bainite, we did austempering. We cool it fast and then we hold it. But if we try to do for the plain carbon steel by the continuous cooling method, then what we'll get? Continuous cooling will not produce you the bainite. Bainite will be formed like this. But if you add the alloy, like we discussed the chromium and ammonium, they will separate out the two noses. Now here you can produce by the continuous cooling. So for the plain carbon steel, continuous cooling cannot produce. Okay, but for the alloyed steel, there we can produce the bainite by the continuous cooling process. If you want to produce in the plain carbon steel, you have to go with the process of Ostempering. Now see, the dash, the quenching rate need to form martensite, the higher the hardenability. Hardenability is ability of the steel to get hardened up to a depth. More is the depth to which it got hardened, more will be the hardenability. So if the cooling rate is very slow, then we can reduce this stresses also, and we can form the the martensite to a very large, so the hardenability will be more. Slower is the cooling rate, fast more will be the hardenability. Okay, the slower the quenching rate, higher the hardenability rate, so we'll go with the slower. Remember we discussed three different, 2, 3 and 4, and we said that okay, fourth one, which is very near to the nose, that will give me the this one, this cooling rate will give me the more hardenability, because cooling rate is very slow. So here, if you someone tell they want the hardenability to be very high, always prefer to go with the slowest cooling rate possible for this particular transformation, which is nose over here. If you are also allowed to put the alloy, then you can shift this entire curve by putting the alloy to the right side, and you can even further lower the cooling rate for the martensite transformation. Okay, now let's go to the last part. Hardenability is specifically about the formation of dash during the quenching. Hardenability is specifically about the formation of the martensite. To what depth you are able to form, that is what defined over here. Okay, so option D is done. Let's go to the next question, question number 15. Match the following. Hardness. It's very easy. It's basic material science, right? Hardness, measure of the resistance to the indentation. That is correct. Option A is the right answer. Also, we can measure it using the Brinell and the Rockwell test, right? So hardness can be done with this. Hardenability. Ease of martensite formation. More is the hardenability, the ease to form the martensite will be the C. So option C is the right answer over here. Quenching. Fast cooling to form the martensite. Option B. Alloying element. Typically increase hardenability. If you are adding the alloying element, what we are doing, let's say before, without adding the alloy element, your curve was like this. Now you added the alloying. Okay, now what will happen, that the entire curve will shift to the right side, or even change the shape and make a two different nose. In the case one where there was no alloy element, the cooling rate, the minimum, the slowest cooling rate, you can go with this. While if you add the alloy, yeah, the slowest cooling rate will be this. Slower the cooling rate, more is the hardenability, and more is the hardenability means that yeah, so you can increase the hardenability of the material. Okay, so fourth one will go with the D. Quenching is B. So this is our, okay, I think I should not write this over here. So this is the answer. First one is also E. Okay, any doubt in this, let me know. If not, let's go to the next question, question number 16. True and false. First one, a plain carbon steel generally have higher hardenability than the alloy steel. Answer is false. Alloy steel will have the more. The concept of hardenability apply to all the materials. No, false. This we are talking from the perspective of the steel. A steel with the higher hardenability can form martensite at slower cooling rate. Higher hardenability can form the martensite at the slower cooling rate. Answer is yes. True. Slower is the cooling rate, higher is the hardenability, ease of martensite formation. If someone gave you, okay, this material, its hardenability is very good, then it means that the ease to which you can form the martensite is there, right? It's very easy to form the martensite in this particular step. Let's go to the next part. Question number D. Hardness and hardenability are interchangeable term. It's false. They are two different things. It's the to, ability to get hardened up to a certain depth. To what depth a material is able to harden. Okay. Hardness is a ability to resist the indentation. It's a plastic deformation. With that, we have completed this question number 16. Let's go to the next part. Now, till now, we have completed the questions which were related with the phase transformations and heat treatment part. Now we are moving to the next part, which is mechanical property of the material. Let's go to the first one, yield strength. We know the stress strain curve is there. After a point, a sample can yield. Right, yield strength. Let's see which of the option will be matching with the yield strength. Resistance to the elastic deformation, ability to undergo the plastic deformation, stress at the onset of the plastic deformation. Yes, yield strength is a stress at the onset of the plastic deformation. So the option C is the right answer over here. Let's go to the Young modulus. What is a Young modulus? If the Young modulus is more, it means that it's steeper. Right, the slope will be higher. Higher slope mean that to get the small amount of deformation. Here in the case 1 where the Young modulus was less, for this you have to apply the low stress itself, but here you have to apply more for the same amount of deformation when the Young modulus is more. So the Young modulus is a ability to resist the elastic deformation. Okay, what we are doing the elastic deformation right now. When till the point we are below the yield strength, we are doing the elastic deformation. Toughness, we know it's the area under the curve, which is the energy absorbed till the fracture. So energy absorbed before fracture, it's the option D. Ductility. Ductility is the maximum stress. No, ductility will be the ability to undergo the plastic deformation. Yes. To how much? What is that? Like some material is very ductile. It means that it can be bended. It can be distorted very easily. Ability to undergo the plastic deformation is more. So it's option B. Maximum stress before necking, we know none of them is going to match here because it's the ultimate tensile stress over here. So this is our answer. With that, we have solved the question number 17. Any doubt? You can please let me know. If not, let's go to the next part, question number 18. Engineering stress consider the changing the cross-sectional area during the deformation. Engineering stress consider the changing cross-section area during the deformation. Answer is no. What engineering stress is? Engineering stress is force per unit area, and the area will be the initial. It is not the instantaneous, it's the initial. So answer is false. Elastic deformation is fully recoverable upon the unloading. This is true. It's a plastic deformation which is not recoverable. Okay. So elastic, if you are within the elastic region, you unload the specimen, you remove the stress, the sample will come back to its original shape, original dimension. Okay. Which we cannot say the same for the plastic deformation. Ultimate tensile strength is always higher than the yield strength. This is true. Toughness is a measure in the Pascal. Pascal is a unit of the pressure, right? So no, even though it's Newton per meter square, we have to multiply meter one more dimension. So Newton meter per meter cube. So it will be like this is what energy, energy per meter cube. Toughness is this energy absorbed, right? So here it's a false. One can say that both of them are more or less same unit only, but the essence of the toughness is like the energy absorbed throughout the process. Now, ductility can be measured by the strain at fracture point. This is true. How much amount of strain has happened? Here the ductility is more. Here the ductility is less. Right? This is true. Plastic deformation typically change the crystal structure of the material. We have seen in the class that this kind of questions has been put to the nature, like we did the characterizations and all, and then found that it's not the case. The plastic deformation is not changing the crystal structure. The phenomena, the mechanism of slip is the one which is helping the plastic deformation to happen. So this is false. Let's go to the last part. X-ray diffraction pattern remain identical before and the after plastic deformation. Yes, this is the result which we have obtained that, and we said that it's not the structure has not changed. So let's write down very quickly: false, true, true, false, true, false, and then true. With that, we have solved the question number 80. Any doubt, you can let me know. If not, let's go to the next part. When a metal is plastically deformed, okay, we cross the yield strength and then unloaded. The unloading curve is, this is how it was going. Now let's say this is the stress strain curve. We deform the material and we get to this particular point. Now we are unloading. The unloading slope will be same as the yield strength. Okay. Parallel to the initial elastic portion. Okay. Option A will be the right answer over here. So with that, we can say that the slope will be same. Even if you load it again, it will follow the same trend. It's just that its yield, now this particular material's yield point has changed. With that, we can say the option A is the right answer over here. Let's go to the question number 20. What microstructure feature appear in the deformed material that support the slip mechanism? So what has happened that we have the material, we have the grain boundary. Let's say this is then undergo the plastic deformation. So I should have drawn the same thing, but it's fine. Additional feature which was appear was this slip line was there. And this is the one, this feature is saying that it's a deformed material. If someone told you that they gave you two material and they told that they forget that which one is deformed and which one is undeformed, just see them under the microstructure. Just see their microstructure, put it in the scanning electron microscopy. If you see inside the grain a slip line like this, it will be dark lines. You will be able to see them. That will be the deformed. If you are not seeing any, it's an undeformed one. So you can distinguish both of them. Okay. So option B here is the right answer. Let's go to the next question. Question number 21. In cubic closed pack structure, the slip plane is which this has been discussed when we were discussing about the dislocations and all, right? So for the cubic closed pack slip plane we are talking about, it's the 1 1 1. We know that slip plane is nothing but the closed pack plane. and close pack plane in the CCP is 111, right? What will be the close pack direction? It will be 110. So instead of slip plane, if I ask you the slip direction, then it will be like this. Now here you can see that the curved bracket has been used while I was using the curly bracket. Doesn't matter. 111, this plane is a family of 111. Okay, so option B we can select over here. One can also put the multiple option saying that 1 bar 1. So that can also be there. Okay, if I instead of this, if I put this, then this will also be the answer. Okay. So with that we have solved this. Option B is the right answer. So we know that in the FCC we have 4 plane like this, and in each of them we have 3 directions. So in total we have 12 slip system in the FCC. Let's go to the next part, question number 22. If slip plane is perpendicular to the tensile axis, the resolved shear stress will be. What we have discussed, two things. Let's say resolved shear stress is equals to the sigma y cos theta n cos theta d, normal to the plane, and it is with the direction, with the slip direction, slip plane and slip direction. Let's say this is the normal to the slip plane, and let's say this is my slip direction, and let's say this is my the stress axis along which I am applying the stress. Okay, so this is theta n and this is theta d. Now if the slip plane is perpendicular to the tensile axis, this plane is perpendicular to tensile axis. What it means? The plane is like this. It's something like this. We can say that. Let's say this is my along which I am applying the stress. This is my slip plane, which is perpendicular to the tensile axis. It means that my slip direction is along this. D is along this. Sigma n is over here. What it means that between the stress sigma and D, the angle is nothing but a 90 now. Theta D is 90. Theta D is cos of 90, we know it's a 0. So overall we'll get 0. We'll not get the maximum. We'll get 0 shear stress working in this particular case. If any of the angle is 0, let's say even if the direction is along, if the direction is along the RSS, along the stress, not RSS, along the stress axis, then again it will be the same case, right? So option B is the right answer over here. Great. Let's move to the next part, question number 23. If any doubt, you can let me know. In Schmidt factor, if the Schmidt factor is this, what is the ratio of CRSS and sigma y? Very easy. We know that tau CRSS is equal to the sigma y time Schmidt factor, which is cos theta n cos theta d. Right. This is given to us as a 0.5. So the ratio between them will be the tau CRSS divided by sigma y will be equal to the 0.5. So will be the right answer. Very easy question. So one need to know. In doing my beta time, I forgot that this is the Schmidt factor, and I made a lot of mistakes in the exam. Anyway, let's go to the next part, question number 24. Schmidt law implies that CRSS is a material constant. This is the Schmidt law, not the mathematical thing which we are saying. Okay, so this is true. CRSS is a material constant. Sigma y is not. The yield stress sigma y of a single crystal is same in all directions. Yield strength. This is what the Schmidt law told, right? Like yield strength is changing, but tau CRSS it's constant. Okay, so this is false. Option B is true. Changing the stress axis orientation alter the CRSS. Here the changing the stress axis. If we change the stress axis oriented, it will alter the CRSS. Just now we discussed that CRSS is a material constant. If you change the stress axis, it doesn't have to do anything. Okay, it will remain constant. So with that, we can say that it's a false. True, false, and false. 24. Any doubt in this question, you can let me know. If not, let's move to the next part and the last question of our today's session. Okay, it's not the last. I have two more questions. This and one more question is there. It's the fill in the blanks type. We have to say that first one. Schmidt law state that dash is the independent of the stress axis. CRSS or yield strength? It's a CRSS. B. Yield strength of the single crystal is dash because it depends upon the this and this. Yield strength of the single crystal is isotropic or anisotropic? It's the anisotropic. With that, we have solved this B. Let's go to this C1. To maintain the tau CRSS constant, an increase in the Schmidt factor required dash in the obviously this is constant. Tau CRSS will be equal to the sigma y times Schmidt factor. Since this is constant, if I am increasing the Schmidt factor, so obviously what will happen? Sigma y will decrease. So it's a decrease. Right. Now the last question. Consider a metal single crystal oriented such a way that normal of the slip plane and the slip direction are making 60 and 35 degree respectively with the tensile axis. Let's say this is my single crystal. This is my sigma y. Along with the stress is there, sigma. And they are telling that theta direction with the n, like slip plane normal, is 60 degree. And the theta, which is with the direction, it is 35 degree. And with the tensile axis. If the CRSS is given, so what is given to us? CRSS. It is 6.2 MPa. Will an applied stress of 12 MPa cause the single crystal to yield? So let's see what is the yield strength of the material. So the question says that these are the conditions. We are applying this much stress, 12 MPa. Will the specimen will undergo the yielding or not? Okay, so let's find the yield stress. If yield stress which is below this 12, then it will be 12 is sufficient enough to cause the yielding. If yield stress is more, then they will not cause the yielding, right? So we know that using this particular equation, tau CRSS, which is equals to the sigma y cos theta and cos of theta d. We know couple of things. CRSS is 6.2, sigma y we don't know, cos theta n it's a cos of 60 and cos of 35 degree. Let's try to calculate this. Sigma y we can calculate from this. What we'll do is 6.2 divided by cos of 60 multiplied by the cos of 35. So what we have got is, so from here we have got the sigma y is equals to the 15.13. So this is the yield strength of our material, this much MPa. If yield strength is this much high, while the applied stress is only 12, so it is not going to cause any yielding to the specimen, right? It will not going to yield the specimen. So next question says that if not, what stress will be necessary? So any stress which is greater than 15.13 MPa will cause the yield to happen. Okay, will cause this material to undergo the deformation. So with that, we have solved this last question. And with this, we can end today's session. Before I end, let me know if you have any doubt in the today's session that we have discussed. If not, we can wrap it up. I have one announcement to make. The announcement is that on 12th of April, we'll have one more class. Like, we have two more upcoming classes uh, on the Saturday, that is 4th of April and the 11th of April. After this, there will be one special class on 12th from 11 to 1 p.m. 11 a.m. to 1 p.m. And that will be based on the entire concept, entire course. So if you face any problem in the entire course, wherever you are facing difficulty, please feel free to join in that session, and we can have a discussion. Okay. So with that, let's meet again in the next class, 4th of April.